Hi, my name is Johannes Postma. I work at the Forschungszentrum in Jülich at the Institute of Plant Sciences, and I'm a member of PhenoRob. And today I'd like to present to you our paper, Crop Improvement from Phenotyping Roots. Roots are at the basis of agriculture production. They're the ones that take up water and nutrients from the soil, and this gives rise to production and in the end yield. So it's a natural question to ask, can we improve these root systems? Here you see an example from Dr. Jan from South China Agricultural University. He selected for beans that root shallow and take up more phosphorus. And he was quite successful. His new lines were able to produce a lot more on these low pH soils. So yes, we can. And there are several other examples in the literature. Narrow xylem vessels to conserve water, thicker primary roots for greater biomass, malate exudates that bind aluminum and avoid toxicity, steeper root angles for deeper water capture, and tolerance to cereal-cystal nematodes. These are a handful of examples that you can find in the literature that show how breeding for root traits can result in new cultivars that have improved characteristics and better yields. But there are just a handful of examples. We found more or less 10 of them. And the question is, why are there so few? And this is because it's hard to observe roots and to understand what the root traits mean in terms of root functioning. There are many ways to observe roots. This goes better in growth chambers in greenhouses where it's easier to harvest roots and somewhat more difficult in the field. And all these different ways yield different kinds of information about this root system. And so we get a very scattered and fragmented image from this phenotyping of what is happening to these roots, how they're responding to the environment. And it's hard to know what these traits mean in terms of water uptake and nutrient uptake. And this is where digital twins can help answering the question. What are digital twins? They are digital versions of the physical, the real thing. Here you see two images from MRI and CT of real root systems. And right next to them, you see the digital version in color. The digital version is a model of the real root system. It's as close to the real root system as we can get it, and it can be used to estimate, for example, nitrate uptake, like you see here. These digital twins are coming ever more like the physical root system. We are able to incorporate more and more traits into them and more processes. Here you see two examples, one for bean and one for maize. And in these examples we incorporated anatomical traits as well as a lot of root architectural traits that determine that root system. Let's have a look at one of those traits. Here you see two images, two simulations, one with few branches and one with many branches. The variation is based on real phenotyping from the field. And when we simulate this variation in lateral branching density, we can estimate what that does to nitrate uptake. What you see here is that on the low fertility, it's optimal to have more or less 5 branches per square centimeter, whereas on the high fertility, it's optimal to have 12 branches per square centimeter. And thereby we can start to understand how branching density interacts with fertility and what the optimum phenotype is. PhenoRob connects the physical and the digital twin. It designs and develops new sensors and robotics to observe many plants so that we can build better digital versions of them, study those digital versions and use them to improve breeding. That way we can speed up the improvement of cultivars for a more productive and sustainable agriculture. I want to thank you for listening, and I summarize: roots are at the basis of agriculture, root rates can be improved, and digital twins can speed up the design. Thank you very much, and bye-bye.